Welcome to MATH QUBE's walkthrough animation on Fourier Transform. In today's animation, we'll be discussing periodicity, non-periodicity, aliasing, and symmetry. For a periodic signal, the Fourier transform gives a big peak at point k, which is equal to the signal's fundamental frequency. Additive mixing of simply leads to additive Fourier transform. Fourier transforms get added here to give a peak at 1200, which is the sum of two individual Fourier transforms. When you append cycles within the same time duration, the Fourier transform gets shifted proportional to the number of cycles appended, which in this case is 8, 16, and 32. When you append cycles by increasing the time for a given signal, then the Fourier transform just amplifies itself at the same position. For a non-periodic signal, the Fourier transform is periodic if the non-periodic signal is valid for a shorter duration when compared to the entire length of your signal. Here, your input signal is valid from 0 to 1000. However, the signal exists only in the interval 100 to 350. This short duration non-periodic signal leads to periodic Fourier transform. The shift in the signal position is not altering the Fourier transform, which is your shift invariant property. The spacing between the Fourier transform peaks is dependent on the non-periodic signal length. Shorter signals tend to be more concentrated than the longer ones. The length of the signal is also inversely proportional to the spacing between the peaks in the Fourier transform. Aliasing occurs due to overlapping of frequency spectrum. The primary cause for aliasing is when fewer sampling points are used to represent a given signal. Aliasing also occurs due to time expansion of signal as it leads to more cycles or contraction in Fourier transform. Every signal formulates as a sum of even and odd signal components. The Fourier transform of even signal is purely real, whereas the Fourier transform of odd signal is purely imaginary. Walkthrough animation on Fourier transform. Summary.